Okay, so sex-linked traits, not nearly as exciting as they sound. Um, these are traits that are on sex chromosomes. So let's kind of go back a little bit and review some stuff. Remember that in a regular body cell, somatic cell, you have 46 chromosomes. 44 of those chromosomes are what we call autosomes. Those are chromosomes that have genes on them that code for just regular body stuff. Okay, whether you can roll your tongue or you have hitchhiker's thumb or widow's peak or whatever, those things are on the autosomes, as well as any genetic disorders. So like there's some autosomal genetic disorders like albinism or sickle cell anemia. Anything like that would be autosomals and the autosomes. But then you also have two sex chromosomes. And so if you're a girl, your two sex chromosomes are XX. And if you're a boy, your two sex chromosomes are XY. And that's in a regular body cell. But if we're talking about a gamete, an egg or sperm cell, that's going to have half the number of chromosomes. Remember, those are haploid. So they have half the number of chromosomes, so they have 23. And so that means that you have 22 autosomes and just one sex chromosome. But if you're a girl, that one sex chromosome is always going to be an X because that's all you have. It's XX, right? So every single egg cell will have an X chromosome. But if you're a boy, some of your sperm cells will have an X and some of them will have a Y. And so honestly, it's boys who determine the gender of a baby because they're the only ones that can give that second X or that Y to make a boy. So when we talk about sex-linked genes, it's a gene that's located on the X or the Y sex chromosome. Most of them that we're going to talk about, well, all of them that we're going to talk about are going to be on the X. We're just going to stick to the X. And remember that any genetic disorder, all the genetic disorders that we talk about, well, let's say most of them, are going to be recessive. That's why you can get two parents, mom and a dad, that have a baby that has sickle cell, but they don't have sickle cell. Recessive traits can kind of hide in families. So when we talk about disorders, we're talking about recessives, and they're sneaky. Okay, so let's talk about one such disorder, hemophilia. Hem means blood and philia means liking of. So hemophiliacs are individuals who cannot clot their blood. Like they don't have the blood clotting factors. They don't make those proteins. And that is a gene that is mutated and it is on an X chromosome. So it's on an X chromosome. And so the issue really is that understand that girls have two X chromosomes. And so a girl has an option that a boy does not. So a girl could have the disease and she would be X little h, because this is recessive. Or she can be completely normal and be X big H, big H being normal. Or she can carry it and still be normal, not have hemophilia. And so then she'd be X big H, X little h. So she'd be a heterozygote. But that's because she has two X chromosomes. But a boy only has one X chromosome. So a boy only has two options. He can either have it, X little h, Y, or not have it, X big H, Y. That is the reason why the majority of individuals with hemophilia are boys, because they only have a 50-50 chance. They can't carry it, so they either have it or they don't. Hemophilia is not the only X-linked disease. You also have color blindness. If you know anyone with color blindness, it's probably a boy. Male pattern baldness. So it does start with the word male, because typically speaking, those are boys. Retinitis pigmentosa is an X-linked trait that causes an individual's retina to deteriorate over time. And by the time they're 20-something, they're completely blind. That, is an X-linked trait, and that's typically in boys. There are quite a few that are boy conditions because they're carried on the X, and boys can either have it or not have it. They don't have the option to just carry it and be healthy. All right, so let's do a practice with sex-linked traits. The normal gene is X big H, and the hemophilic gene is X little h. So remember I told you that most disorders are recessive. And so hemophilia is definitely recessive. Colorblindness is recessive. Male pattern baldness, recessive. Okay, retinitis pigmentosa, recessive. These are recessive traits. So typically speaking, they're recessive. All right, so here's my male. I have an X and a Y because that is a male, and he's normal. He's got the big H, so he's normal. And over here, I've got a female, and she's still normal. She's healthy, but she has one H, big H, sorry. She has one big H and one little H. She's a heterozygote, or what we like to call a carrier. So she carries the gene for hemophilia, but she is herself not a hemophiliac because the law of dominance says the big H is going to win. All right, and so we're going to do the same thing that we always do. And for some odd reason, I put the little H in front of the big H, but you can, it doesn't matter. You guys know little H can go in front of the big H or whatever. But here's my girl. I separated out those alleles. Law of segregation indicates that we separate, okay? And then again, my boys. And so here are her egg cells. She's got this gene in one egg cell. So this chromosome with this gene in one egg cell, and this chromosome with this gene in the other egg cell. And then my guy here, he's got this X chromosome with this gene in one sperm cell. And then in another sperm cell, he just has the Y. All right, so let's see what the possibilities are when this sperm cell enters this egg cell, what type of baby you'll get. So when this happens, X and X make a girl, and this girl has one big H and one little H. Remember, law of dominance says that she's normal. Okay, so that H, that big H is normal. So she's going to be normal, but she's a carrier, and so she can pass it on to her child. She can pass this little H onto her child. This girl, big H, so X big H, X big H. This girl right here, she's completely normal. She can't even pass it on. She doesn't have it at all. Okay, so those are our two girls. And then the boys down here, XY, XY. This first boy right here has a big H, and so he's completely normal. Like, he's fine. But this little boy right here, he's a hemophiliac. Notice how he's got one little H, and so does his sister right here. She's got one little H, but she's normal, whereas he's sick. That's because she's got the other big H to help her out, but he cannot have the other big H because he only has a Y. And so that having been said, he is definitely a hemophiliac, and that's why we have mostly males that are hemophiliacs, because they do not have the ability to simply just carry it and still be normal. All right, so our genotype ratio gets really long because we have one X big H, X little H, one X big H, X big H, one X little H Y, and one X big H Y. So we have one of everything. Our phenotype ratio is still very long itself. So we've got one completely normal female, like she's got big H, she can't even pass it on. And then we've got one that's a carrier. Reminder, she is still normal. Like, she's still healthy. She's fine. But she's a carrier, which means that her child can end up with hemophilia, and probably a boy. Not 100% all the time it's a boy, but like 95% of the time it's a boy. Okay, and then one normal male and one hemophilic male. Okay, so now the probabilities get weird, because if I ask you on a question and a test, I say, okay, what's the probability of having a child that is a hemophiliac? Well, you've got 4 children here, and there's only one that's a hemophiliac, and so you would say 1 out of 4, a child. But if I ask you specifically about the boys, there's only 2 boys right here. So if I said, what is the chance of having a boy that is also a hemophiliac? Well, that's 1 out of 2, so that makes that 50%. So you have to be careful about how you read the question, because if it's a child, then yes, 25% works. But if I ask specifically about the boys, and there's only 2 boys, that means that it's 50% or 1 out of 2. So it's 50% or 1 out of 2 hemophilic males, 1 out of 2 normal males. Okay, so specifically if the gender is there, you have to be very careful about your answer, because there's only 2 of those in that Punnett square. Another thing that you need to be careful with is that when you're crossing a male with a female, you need to make sure that it's truly a male. Okay, so while there's nothing wrong with it, you cannot cross an XX with an XX. You can't produce children that way. So you have to make sure that you're crossing an XY with an XX. And you can't cross an XY with an XY. Perfectly fine, but you can't make children out of that match. So if you end up with a YY in your Punnett square, yeah, there's something wrong. Okay, so you cross the male with the male, and you can't make children that way. So let's not try that. All right, so let's try another example. I'm gonna cross a hemophilic male with a homozygous normal female, and so he's X little h. Again, he only has one option because he only has one X chromosome, so he's X little h, and then Y, and then she's completely normal. She's got big H, big H. You know, she's totally normal. This is what that looks like. So I end up with the first child being X big H, X little h, and that's a female, and then X big H, X little h. And so both of these females are going to be normal, so they're healthy. They don't have hemophilia, but they each carry that mutated gene that they could pass on to their children. All right, but then let's look at the boys, and boys are X big H Y, X big H Y. What I want you to notice about the boys, and first of all, they are normal because big H means they're normal. Secondly, they cannot carry it, so they have no way of passing that on to their children at all. Third, I want you to notice who they get their X from. They get their X directly from their mom because they get the Y from their dad. And so if this child here was a hemophiliac, the person he could blame, I suppose, would be the mom, because the mom is the one that gave him the X. Okay, so it's moms that give it to the sons. But the moms may not necessarily have the disease themselves. So genotype ratio is 2 of both, so 2 X big H, X little h, and 2 big H, X big H, Ys. Phenotype ratios, I've got 2 carrier females, still normal, they're still normal, and 2 normal males. Okay, and so here are our probabilities right there. Okay, so now I want you to go through, and I want you to practice with the calico cats. Practice that and see how well you do on that. So that's how sex-linked traits work.